Well, so we're talking about normalized Laplacian. There's a few things I do want to talk about the normalized Laplacian for. And this goes back to some comments I made last time, which I'm going to justify more next week, but still I want to talk about things. And which is to say, how do we look at subsets? So, in other words, suppose that we have U is a subset of V of G. So I have a collection of vertices. And I want to say, how do I measure them? What's the right type of measurement? Well, the old way to measure things is to say we can just count how many things there are in U. So that's the size of U. So this is our vertex-centered viewpoint. Now, this is perfectly fine and reasonable if everything were the same, but not all vertices are the same. So we're going to have a new idea, which we're going to introduce, called the volume. And this will be our edge-centered way of looking at things. And so how do we do it? Well, the definition for a volume of a subset of vertices is you sum over all the vertices in your set U of the degree of V. So that's our volume. So essentially what you should think of is you should say, okay, the volume is how many connections are there inside U, or how many connections does U have? Now, I can already see there are questions.
Are we not dividing by 2?
We are not dividing by 2. That's a good question. There's also an implication in that question. I don't know if you...
Are we counting connections from U to not U?
Okay, so that's another implication that you want to ask, which is to say, when I have, of course, here's the whole graph, and we're advanced graph theory when we draw blobs. And so then we have a small part, here's U. Well, there are some edges that cross out of U, but then there are some edges that stay within U. And the answer is no, we aren't interested in differentiating between these right now. Now, there are some times when you want to look at the edges that go from inside U to outside U. And such as next week, we'll take a look at that. And that gets into what are known as isoperimetric problems, basically wanting to get good cuts. And so no. Now, you might say, well, wait, if we're adding the degree, you might count some edge twice, because if it's an edge that goes from a vertex in U to a vertex in U, well, then you added that edge twice. And that's okay. We're going to be fine with that. And because, one, it makes the math easier to write, and two, it makes things easier to prove. And so oftentimes, that's how math goes, is what's easy to prove, and that's the way we'll approach things. All right. Good. Now, we should talk about, in addition to the volume, we've mentioned a few other things, and which I'll say E of UW. So I might have another set W is equal to what? Well, I have to be careful here, and let's see how to write this. So this is, well, it's the number of edges between U and W. That's how we should write it. Now, I've drawn it this way. We're not actually going to have overlap today, but we could have overlap at some point in the future. And inevitably, someone will say, well, wait, what about something that's an edge in both u and w. What do you do there? And the answer is?
Count it twice.
Well, yeah. Well, I should say the answer is whatever we choose it to be is the correct answer. And for us, we will choose it to be, we count it twice. And so we see it as an edge between u and w in two different ways. All right. So now we're going to go and do a quick recall. And let's see if we can do this. You have your notes. That's helpful. You also have me. I can be helpful sometimes. So equitable partitions, and let's talk about for the adjacency matrix A. Because, okay, we've talked about this before. And what we did was we took our vertices of our graph G.
So, are we counting those edges twice? No.
Which edges?
Between U and W.
If it's in the overlap, those get counted twice. If it's not in the overlap, it gets counted once.
Oh, got it. Okay.
So, and there'll be I'll point out next time why that's a very convenient convention for us. And essentially what it boils down to is if we think about things in terms of the adjacency matrix, then what we're doing is you're basically adding a certain subset of the adjacency matrix, saying what's the total. And so you say, fix the rows of U, fix the columns to W, add that subset. And then you say, okay.
Okay, sorry. And we may have an edge from U into the overlap. Is that one counted once or twice?
Only, okay, wow, you're really getting after me today. All right.
Yeah.
Okay, cool. Well, then we'll put that aside for a few minutes. And I realize now that for our discussion, we should have one other thing we should talk about, which is we should move from simple graphs to weighted graphs. So let's do that while I'm not stalling for time. I want to point out, we'll answer your question semi-definitively. Okay, so for weighted graphs, we weight the edges. And so W, U, V. All right. Well, what's the degree of a vertex V in a weighted graph?
Just the sum
The sum of the weights.
Yeah. So it's the sum of the weights of everything that's a neighbor. So essentially, you can think of a simple graph. The weights are 0 and 1. And then so in the volume, you're essentially it's the sum of all the weights. Now, so how could we define the edges between U and W? Well, if we do it in terms of a weighted graph, what's one way we can think of it? We could say we're going to sum over all U in U, sum over all W in W, and the weight U, W. So that's a way you could reasonably define, the edges in a weighted graph, and even the edges in a simple graph. Now, the question you have is you say, okay, when will things show up once? When will things show up twice?
Yeah.
And if I have, let's see, what's your scenario you want to check? So here's U, here's W. Well, if we're in the overlap, then what will happen is, it depends on, do I think of the first vertex as being in U or as being in W? Because essentially I have a choice to which one's in U and which one's in W. Now, if I have something here, is there a choice for both of them? Well, this vertex in the overlap, sure, you could think of it as being as in either U or W, but this one has no choice. It has to be in U. And so that one is only, the only time it'll show up in the combination is that when it's in W, so it's only counted once. So it's only the overlap where you're doing your overcounting. And so that's one way to think about what's happening. And in terms of your matrix, if we just think of our weighted adjacency matrix, you say, well, look, I have something in U, then I have something in W, and then what you're really doing is you're taking this little sub-matrix and you're tallying it up. And, well, it just might happen that you might overlap a little bit with the mirror, and so, but, all right. So, okay, good. Whew. Equitable partitions. Now we can get back into that. And, okay, so recall equitable partitions, and maybe perhaps we'll do a recall by example. What was the goal for equitable partitions? We were splitting our vertices up. What made them equitable?
Any vertex in one chunk has the same number of edges to other chunks.
Ooh, that's nice. And so you're right. So what you can do is we can come up with numbers, and I think we use B, so I'll use B sub I j. And what this represents is that for pick any vertex at all in V sub I, it has exactly Bij neighbors in Vj. So it has the same number of neighbors. All right. So what do we do? Well, let's pick on a graph, and I'm going to do the Peterson graph again, not because there aren't other graphs. There are, in fact, infinitely many other graphs besides the Peterson graph, but this one just happens to be easy enough to draw and nice enough to talk about examples. Okay, do you remember what our partitions were when we did this before? Now, there are multiple equitable partitions for graphs. Every graph, you can do an equitable partition by just making every vertex its own partition, its own V, Vi. I'll give you a hint. V1 was a single vertex. What was V2?
The neighborhood of V1.
That's right. It's everything that connected to V1. That was V2. And then the rest. Good. That was our V3. And what we would do is we said, all right, what we can take now is we'll take our matrix of these subscripts. All right, so I'm going to create a new matrix B, and all right, so for any vertex in V1, how many neighbors are in V1? 0. For any vertex in V1, how many neighbors in V2? 3. For any vertex in V1, how many neighbors in V3? 0. Good. Okay, next row. For any vertex in V2, how many neighbors in V1? 1. For any vertex in V2, how many neighbors in V2? 0. For any vertex in V2, how many neighbors in V3? 2. All right. Now come down to V3. Pick a vertex in V3. How many neighbors in V1? 0. And pick a vertex in V3. How many neighbors in V2? 1. And pick a vertex in V3. How many neighbors in V3? 2. And the moral we got to was the great aha. The eigenvalues of B are eigenvalues of A. And we did some hand waving here. But ultimately the proof comes down to saying that you can take your eigenvectors for B and essentially lift them up to eigenvectors of A. Okay, but there's a trade-off, something we've lost along the way. And that is, if you look at B, it's not necessarily symmetric. So B need not be symmetric. And so what we're going to do is we're going to do equitable partitions again, but now for the normalized Laplacian, and we're going to do it in a different way. In a way where we do get to preserve. And, all right. Preserve symmetry. Okay. So, are we good with equitable partitions for A? All right, we're going to come back and draw this same picture in a few minutes, and we're going to talk about it. So, here's the idea. So, for equitable partitions for the normalized Laplacian, we're still going to have a partitioning of our vertices. And by the way, it's not that the case where it's like, oh, if you're an equitable partition for A, you may not work for the normalized Laplacian or vice versa. If you work for one, you'll work for both, and what we're about to talk about, especially if you start with a simple graph. So we still have our vertices split into pieces. And what do? Well, now we have to talk about the weight. So we're going to form a new graph, and H. And this is going to be an undirected graph where it has vertices.
We have hills.
Oh, great. V1, V2, up to Vk. And our big aha, I need to tell you what to do with the edge weight between Vi and Vj. So sorry, I said E, I meant to say W. All right, let's just start again. And the edge weight from Vi to Vj is equal to the number of edges from Vi to Vj. And you can do this for weighted graphs where you weight the edges. Okay, so let's talk about it. Now, so far, I haven't made any claims. And so there's nothing that you can say, aha, this can't be true. Because all I've said is, here's a definition. And you know, definitions, you can't say, oh, that's a false definition. No, it's my definition. You can say it's a bad definition. That's okay. But you can't say, you know, it's a wrong definition. It reminds me once when I was at a talk in grad school, and someone was writing a theorem up on the board, and they were halfway through writing the theorem, and then there were starting to be like strong discussions about whether this was true or false. And then I had to point out, they actually haven't stated the conclusion of the theorem. All they've stated so far are their assumptions. We should see what the conclusion is before we argue whether or not this is good or bad. And so, you know, hold on. Let's see what happens here. Okay. So
H can have loops, right?
yes.
Okay.
Yes, H can have loops. That's all right. We're okay with that. And you might be wondering how to handle that, but the answer is it works itself out. That's not a very satisfying answer, is it? But that's all right. You still work it through in the same process where you just think of, D minus A, and then you take the normalization on both sides. So once you start allowing loops, we haven't allowed loops yet. Once you start allowing loops, what can happen is that your diagonal entries might be smaller than 1, essentially is what it turns into. But that's okay. That's all right. So for this graph, we'll do a similar splitting up. So we have our V1, and then we'll have our V2. And then we'll have our V3. And we're going to form a new graph. And the new graph, well, it has 3 vertices, V1, V2, V3. Okay, well, you've mentioned loops, so we might as well just go ahead and just double check. Is there a loop on V1? And if there is, what's the weight? No loop, because there's no edges from V1 to V1. All right, from V1 to V2, how many edges are there? There's 3. So we're going to put a weight here, 3. Now notice the number of edges from V1 to V2 is the same as the number of edges from V2 back to V1. And so there's symmetry. And so I don't have to worry about, I have to have an arrow going one way versus another. It just works out. All right, is there an edge from V1 to V3? No. Is there a loop on V2? No. All right, is there an edge from V2 to V3? Yes. All right. So, what's that going to be? Well, you have to count the number of edges. How many edges go between V2 and V3? 6. Yep, exactly. 2 for each vertex in V2. Or you could say 1 for each vertex in V3. All right, finally V3. We don't need to check V3 to V2, but is there a loop on V3? Yes. Okay, now is our danger point. So this is the place where if you make a mistake, and I've made mistakes before on this, it's sort of like, okay, remember, we have to count edges twice. Or do we not? I don't know. Let's find out. The easiest way to find out is you do an example, and if it works, then you're like, yes, I always meant for it to count twice. And if it doesn't, you say, well, in this case, it should actually only count once. I know it doesn't feel like that's the way math should work, but I got to be honest with you. It's kind of the way math works. So you always get to see math that's been polished. But most math doesn't come polished. Okay, so V3, V3. What's goes here? Yeah, that's the question we have. Is it 12 or 6? I think it's 12. It's 12. We're good. Now you might be thinking like, why do you think it's 12? Because from my perspective here, I'm looking at the ratio between the edge V2, V3 and just the edge V3, V3. And I'm thinking, okay, if I pick a vertex, I see that I should have 1 to 2 ratio of edges from V2 versus to V3. So I want to see like a 1 to 2 ratio of the weights. So this feels right. So okay, good. Phew. Now, of course, the ultimate test, and we make a claim and then we check it. So what's the claim? So the claim is the following. The eigenvalues of this graph here of H are also eigenvalues of G. So The eigenvalues of our smaller graph are eigenvalues of the big graph. A lot like it was in the case when we were dealing with the adjacency matrix. But now it's a little bit cleaner. Well, let's see. Are we bold enough to check if this is true? First off, let's talk about what happens for the normalized Laplacian for this matrix. And so if we think about it, we can start building it up. So for the adjacency matrix, we would have a 0, 3, 0, 3, 0, 6, 0, 6, 12. That would be the adjacency of this weighted graph. Then d minus a, well, to find the degree, it's the same as the row sums. So it would be 3 minus 3, 0, minus 3, 9, minus 6, and 0, minus 6, and
18.
Right, 18 minus 12,
Oh,
6. Okay, so that's not the normalized Laplacian. Now we multiply d to the minus 1/2 a d to the minus 1/2. And this might take a second. Okay, so our degrees were 3, 9, and 18. And okay. So we'll see how good our patience is. We seem like patient people. I hope that holds true. So, all right. Well, what do we get? Oh, someone's using their, okay, technology. So,
How are you multiplying first?
well, let's just do them all at once, right? Well, but think about this way. When you multiply by a diagonal matrix, on one side you're scaling the columns, and one side you're scaling the rows. And so I believe this is the column scalar. Okay, good. Now we've had two people agree with me and one more. So it must be true. So this is the row scalar. And so we don't even have to worry about the non-zero entries. So we take 3, scale by 1 over root 3 and 1 over root 3. That leaves us with 1. And then this minus 3, well,
that's L, not A.
Oh, sorry, this is d minus a.
Yeah.
Sorry. You're right. Got ahead of myself.
I was just confused for a bit.
You're probably thinking, wouldn't it have just been easier to take I minus d to the minus 1/2, a d to the minus 1/2? Yes. Not probably. It would have. But, okay, so now for this entry, well, we're scaling by 1/3. That's pretty easy. Then it's scaled by 1 over root 3. So that's minus 1 over root 3. And then 0 is 0. Here, well, we have, it's symmetric. I don't even need to worry about it. Don't have to think. For 9, we're scaling by 1/3 and by 1/3, 1. Then for this minus 6, well, we're scaling by 1 over root 18 from the column and 1 over root 9 from the row, which makes a number. Yes, it does make a number. Okay, minus 6 times 1 over root 9 times 1 over root 18. Now, the good news is this is minus 6 times Isn't this fun? You can pull out
1 over root.
and 1 over root 2, yes?
Yes.
Okay, so that leaves us with, well, okay, so,
Negative root 2 over 3.
Yeah, negative square root of 2 over 3.
yeah, great. See? That's wonderful. Negative square root of 2 over 3. And, of course, we've got symmetry, so we're doing wonderful here. That just leaves us with one more entry. And here, we're scaling by 1 over 18. And, whoops,
Yeah.
that should be a plus 6. And so that leaves us with a positive 1/3, because that should have been a plus 6. And see, there we go. So now, if you compute the eigenvalues of this matrix, then you'll get some nice numbers. And do we?
But are you sure?
1 and 2/3, 2/3 and 0.
Sorry, what is it?
1 and 2/3.
You mean like 5/3?
Yes, sorry. My head hurts.
No, it's okay.
5/3,
So eigenvalues are 5/3,
2/3,
2/3,
and 0.
and 0. Yes, exactly. Exactly. That I agree. Of course, we can check. The sum is 2 1/3, or 7/3, and because that's the trace. Now, you might say, is that what we should have gotten? Well, do we know what the eigenvalues of the Peterson graph are for the adjacency matrix? Yes, because you did homework, so you were supposed to find them. And then we did it in class, so we found them again. I'll give you a hint. One of them should be 3.
Yeah, because it's regular.
3, 1, and 0, or 3, negative 1, and 0?
It's not 0.
Negative 2 and 1.
Okay, negative 2 and 1. Okay, yeah, I believe that. So those are the eigenvalues for the Peterson graph up to multiplicity.
Yeah.
Okay, so now for normalized Laplacian, because it's regular, you first scale by the degree. Okay, so we'll scale by the degree. So 1 minus 2/3, and then 1/3. So this, then what you do is you negate them, because you have the minus a, and that's been normalized. So minus 1, 2/3, and 1/3. And then there's one more thing that you do, minus 1/3, which is you add 1. And what do you get? 0, 5/3,
And 2/3.
and 2/3. So if these are the eigenvalues of the Peterson graph up to multiplicity for the adjacency, 3 minus 2, 1, then the eigenvalues for the Peterson graph up to multiplicity for the normalized Laplacian are 0, 5/3, and 2/3, which are what we just got. So the claim is true for the Peterson graph. And if we know anything about graph theory, once something's true for the Peterson graph, it's just true. You know, it's the ultimate tester. That's right. Every graph is 3 regular. So it's true for the Peterson. It must be true. All right. So now that we've actually made the claim, we will try to prove this. And I hope we will get through the bulk of it. A lot of it was just building up the right notation. So we'll call this a sketch of the proof. And most of it is not too bad. So we want to somehow show eigenvalues of H or eigenvalues of G. That's our goal. And when we said this, we forgot to add, and I'll add it now for anybody who just looks at the scan notes for the normalized Laplacian. Okay. So we're going to construct a similarity type matrix. So we'll call it S. And it's going to follow the following rules. We're going to have dg to the 1/2. And then we're going to have a matrix here which I'm going to explain, and then we're going to have dh to the minus a half. Okay, now in this matrix here, this is, we're calling this S hat, and we want to think about the size. So G is the bigger graph. And so in terms of dimensions here, that means that, let's see, if G is the bigger graph, this should be a tall, skinny graph. Am I doing this right? Good, all right. It's been a while since I've taught linear algebra. I should do that sometime. And I love the people using their hands. I think that's great. I think it's a wonderful, because that's what I would do. I'm a firm believer. Use your hands and make it impactful. Now, what's going on here? So for S hat, I want to dig into it. We're going to have a vertex. So this is a vertex in G. And then we're going to have our collection of vertices, our Vj, our partition. So this is our partitioning. And this is going to, which, remember that when we do a partitioning, these are our vertices in H. So what would make sense? If I have a vertex in G, and so my rows are indexed by vertices of G, and my columns are indexed by subsets of vertices, what's the logical thing to do?
Little one if that vertex is not partition.
Exactly, yes. The logical thing to do is we're just going to have this entry here is 1 if V is in V sub j, and 0 if it's not. Okay. So in some sense, this is sort of like the incidence matrix. It's an indicator of what's going on. All right, good. Now, if we do our same multiplication here that we did previously, so remember when we talked about previously, we said, well, if we have the middle and we multiply left and right by things which are diagonal, we just have to figure out what's going on with our scaling. Then what we can say is our Sij, so you should think of it as vertex I, subset of vertices j. And what would that be? Well, it's going to be one of two things. It's going to be 0 if something's not true, so 0 else. And then, well, it's going to be this 1, but then you have to scale on the left and the right. Now, from the left, we're going to have a positive the degree, square root of the degree. Well, positive, this is exponent. And the right, the negative exponent means it's going downstairs. And so this becomes the square root of the degree of vertex I over the volume of VI. And this is if volume VI, this should be volume VJ. Okay, this is terrible notation. If I is in VJ. All right? So the way that you capture your degrees in H is you sum up. That's why we have a volume term. Okay. Cool. Any questions so far? All right, I'll ask a quick question. Are these rows perpendicular to, sorry, are these columns of S, are they perpendicular?
Columns where?
So the columns of S
S hat?
are well, and S hat, you can answer that too. Are they perpendicular to each other?
Can we be in one group at a time, right?
That is correct.
And then
Yes,
yes.
yeah, because where something is 0, or more particular, something is non-zero, in the other columns you have to be 0. And so the dot products of any columns are zeros. Now, once you've added these normalizing terms, are they not just orthogonal? I claim they're orthonormal. Well, when you take a dot product of the column with itself, you have the square roots go away, so it's the degrees over the volume. And you sum up the degrees, but the sum of the degrees is the volume. And so we have a nice orthonormal collection of vectors. Okay, cool. Well, so now we're going to do some computations here. We're going to take our Laplacian matrix for G. We're going to multiply it by this matrix S. Well, we know what the Laplacian matrix for G is, and we know what S is. So let's write down what we know. So Laplacian matrix for G, that's our d to the minus 1/2 times our degree G minus the adjacency in G, d to the minus 1/2. And I'll put subscripts everywhere just so we don't lose anything. Times S, which is our, it's degree G 1/2, and then times our S hat, and then we have degree H to the minus 1/2. All right. Well, good news. The middle two terms cancel each other out because we have to the minus 1/2 times to the 1/2. Life is good. All right. Well, so what does this become? This becomes dg to the minus 1/2 times dg minus ag times our s hat times dh to the minus 1/2. So our next goal is we want to understand what's going on. So I'm going to look at the entries here. All right. Ooh, I don't know if we'll make it, but we'll give it a good try. So LGSIJ. Well, I claim there's a couple of cases. Well, first off, we're going to be multiplying on the left by 1 over the square root of degree I. And then we're going to have our degree degree in G of I. I don't know why I put DI here and then I spelled that out there. I should not do that. That's just bad form. And, okay, then minus our sum of all our pieces. Sorry, this will all make sense in a second here. VK in VJ W VI VK times, from the far right, we have our 1 over square root volume Vj. Now, what's happening here? The terms on the far left come from the degree here. The term on the far right comes from this term there. And then it's just a matter of carrying out the multiplication of these two. And so the S hat, you'll notice, is a bunch of zeros and ones. And so you're capturing up this one piece on your D sub G, and then you have terms from A sub G. Now, this part is only true if V sub I is in V sub J. Well, what happens if it's not that? Well, it's pretty much the same. The only thing that happens if you're not here, what goes away? Just one thing goes away.
Yeah, that sum.
The degree.
The degree.
Essentially, this just completely gets missed, because you'll miss it out when you multiply by s hat. So 1 over square root of di, and minus the sum vk and vj. This vi, some of the edge weights, 1 over square root volume vj, and this is the other case. All right. Well, now most of this is going to be a matter of simplifying. Okay. So, I want to look at these two pieces together. The claim here is if Vi is in Vj, there is a connection between these two pieces. What you should think of is that in an equitable partition, all your vertices should look the same. And that's the key thing. And so in particular, we have the following. Our di, well, that's our volume of Vj over the number of vertices in Vj. So everything looks the same. Now, what does that allow us to do? Well, that allows us to say the following. This becomes, if we work it through, we can say that we have, 1 over the square root of just the size of your Vj, then, all right, I'm definitely skipping some steps here. So 1 minus, now here, what are we counting? Well, we're going to end up with the edges between Vj and Vi over the volume of Vj. All right. And this is if Vi is in Vj. Otherwise, we get 1 over square root of, Vj, and then it's just minus the edges. But we ended up with a square root. Sorry, there's a lot of details here, and due to time, I can send you a PDF that you can peruse when you are like looking for something to read. But here's the punchline. Before you run out the door, the moral is this becomes SL hat. Or sorry, S Laplacian of H, Ij. So when we multiply on the right by S versus if you multiply on the left by S and compare entry-wise, we get the same thing. Well, what does that tell us about these two matrices?
That they right in this of one or the left in this of the other.
Similar.
Yeah, they're similar.
Well, they're more than similar. What are they?
Hundreds.
Well, they're the same, right? Because we put the Ij entry is Ij entry. Now, does that mean that they're similar?
Oh, wait, no.
Not yet. What's the problem? What's this S? It's not square.
It's square. Yeah, I was like, hold on, it's not invertible.
So you might say, well, you have a problem here because we don't have an invertible matrix. So you know that LG times S is SLH. And so you say, okay, what can we do? Well, the answer is we make it a square matrix. So how do you make something into a square matrix? Well, you take S and you say, this is great, and you add in more columns. And just add some orthonormal columns. And now you use that new matrix, that square. And when you do that, what's going to happen is you're going to have not just LH on this side, but you'll have the following: LH, and then 0, matrix, other matrix, other matrix. This now is square. It is invertible. So what's true is that these matrices are similar.
Yeah.
So they have the same eigenvalues. And the nice thing is in that this matrix,
Block triangular.
since it's block triangular, the eigenvalues in this matrix of the Laplacian of the smaller graph are eigenvalues of the bigger matrix, and therefore they're eigenvalues in LG, Laplacian for G. So that's the idea. All right.